Hi, it's 6:30 and good evening. My name's Steve Peats and I'm chair for the home county South East. And just before I introduce our presenter this evening, have a couple of short announcements. First, thank you for taking the time to attend this evening, and thanks to Ella from Regions Executive at Balham, providing all the much needed technical and admin support for this meeting to go ahead. And just really a reminder that CIBSE regions are in place to support the charitable objectives of the institution, encourage the intellectual welfare of members, and improve the understanding of building services engineering among other professions and society in general. And this is normally carried out by organising periodic meetings like we have tonight and other activities related to the theme of the built environment. So if you've got future ideas for meetings or activities, please let me know and email me. I'll leave my contact details in the chat box. So just a couple of housekeeping points. If you have your cameras turned off and your audio on mute, this will help transmission. And if you have any questions, please put them in the chat box at the end of the presentation, and I'll read the questions to the speaker and ask the speaker to respond. So now I'd like to introduce Stuart Heron, who's Sales Director, UK and Ireland, and the CPD is on flow and pressure control for potable water systems. Stuart, thank you for attending, and over to you.
Well, thank you very much, Steve, for the introduction, and thank you for the invitation to have this opportunity to present to such a high caliber audience this evening. So a very quick introduction. Hopefully the majority of the attendees will be aware of who we are as Flamco, but just to give you a very brief insight to who Flamco are and who we belong to, I'll give you a couple of slides on the introduction of the company. We're part of a large organisation or a group called the Alberts Group. Alberts are a Dutch organisation based in Utrecht, close to Amsterdam, and they're a true global group with presence in many countries. We're now present in just coming up to 40 countries throughout the world. So we turn over a £3 billion sterling turnover per annum, and such is the size of the business that we split up the business into different divisions or business segments. And under these segments, you would recognise some of the very reputable brands such as Pegler, Yorkshire, and a few other brands you will also recognise within the industry. But for us as Flamco, we're an integral part and the lead company within hydronic flow control. Also under the hydronic flow control umbrella are other brands such as Comap, which is the MLCP piping solutions. We've got MIBUS for heat interface units, and we've recently acquired a company called Sentinel, who are the specialists in water treatment. So we've got a vast array of expertise within our business segment. And if we look at the sectors we are present in and we are active within, it ranges from the residential. So we're looking at your piping solutions, your MLC pipe and your heat interface units, right through to your mission critical, which is including your data centers and your hospitals. And for tonight's presentation, the healthcare sector, hospitals, care homes, is going to be one of the key areas of focus for the content within this presentation this evening. So just to finally give you a bit of a lowdown on what our core competencies are within Flamco. For many years, we've been renowned for experts within the boiler room, within a specialist focus in pressurization, expansion, air and dirt separation. But as we've evolved and strengthened as a group within the last 5-10 years, we're now proud to say that we're more of a technical solutions company. Our route to market is mostly via the specification or through design and value engineered design and build installations. But we're now proud to say that we're a technical solutions company offering products from source to emitter. So if we now get into the body of the presentation, and tonight's CPD is all about potable systems and how we can mitigate the risk of Legionella within our systems. So throughout the presentation, I'll introduce the legislation and the relevant standards pertaining this Legionella control. And throughout the presentation, we may be a little bit repetitive, and there's a common theme, which is all about how we can avoid stagnation of water and how we can reduce the amount of dead legs in our systems. We'll be giving you tips and giving you pointers on best practice and system design to adhere to the relevant standards and best guidance. And then we'll talk about specific product technologies which help us achieve and comply to these standards. So the three main technologies we'll be talking about tonight include expansion vessels, a flow-through expansion vessel, pressure reduction valves for the flow control in our systems, and thermal balancing valves for the hot water recirculation systems. Then we'll finish off with a bit of a summary on some of the key industry issues and, of course, some of the tried and trusted solutions by Flamco and others. And then we'll have an opportunity at the end to invite you guys to ask any questions, and I would highly encourage you to do so. So we get straight in, and we're going to touch on some of the standards, legislation and best guidance which we need to adhere to as engineers. If we've a blank canvas, if we've got a scheme drawing or scheme on the design table, what we need to look to for guidance on how we can ensure that we're mitigating the risk for waterborne bacteria such as Legionella. And we can find that in some of the approved codes of practices, namely the L8, in the main body of the L8, and also the addendum in the HSG 274 Part 2. Both of these documents really address and give you clear guidance on how we feel it's the best way to mitigate the risk of Legionella within our hot and cold water systems. And if you think about it, this is all about potable water. And potable water is all about water being fit for purpose for human consumption. And such is the importance, it carries that health and safety banner, and such is the importance of making our systems correct that it comes alongside a lot more legislation and guidance than, let's say, their heating and chilled water systems would. So if we look at the healthcare sector in particular, what we should be looking for guidance is the HTM, the technical memorandums, and the healthy building notes. And this can be found, the most relevant section within the HTMs for healthcare can be found in the HTM 0401. And Part A is probably the most relevant part of the document for our attendees this evening, because it addresses the design and installation and commissioning of our systems, of hot and cold water potable systems, in order to provide the best possible designs to mitigate this risk of Legionella. So the next couple of slides, I'm just going to pinpoint some of the key points throughout this legislation and guidance. I'm just going to pull out some of the extracts, some of the key important parts. And one of the first points I would like to make is all about making sure that our hot water is hot. And within the guidance and the L8 documentation and regulations, it stipulates that our hot water has to be hot within 1 minute of turning on the tap. And what is hot water? Well, it's 50 degrees for all sectors, with the exception of healthcare, which is 55 degrees. So within turning on your taps or outlets, you've got to achieve those temperatures within 1 minute. Now, balancing of the hot water systems is now a critical part of the regulations and the recommendations. And here, point 237 states that the balance in the hot water system flow and return circuits is critical. And to achieve the first point in the slide here, if we don't have a balanced system, we're not going to achieve hot water within 1 minute of turning on the tap. So balancing our systems is a critically important topic, which we'll touch on later on in the presentation. So we still, within the documentation, we still endorse temperature. And as a building regulation, as part of the water regulations, we stipulate that stored water has to be at a minimum 60 degrees and circulated no less than 50 degrees, 55 for the healthcare premises. And a couple of slides will explain why those temperatures have been selected. And again, throughout the documentation on several areas, we stipulate that the hot and cold waters should be designed. I'm just going to move the screen here. Without dead legs Or if this is not possible, which we all know as designers, it's near impossible to design a system without dead legs, but we got to limit the length of dead legs wherever possible. So we've got to reduce those dead legs. Okay, temperature control, again, is endorsed throughout these extracts, throughout the L8 and the HTMs. And this is really a thermal disinfection module, and this is still a very common method or strategy which clients and designers would utilize to ensure that we keep on top of the bacteria growth within our systems. And this is really just implementing, as part of a risk assessment, a thermal disinfection strategy throughout the year to ensure that the temperatures are inflated such as to such a level that it kills off the bacteria within the systems. And again, just to highlight, and sorry if I'm sounding like a broken record, but again, in several parts of the regulations, it's about regular movement of water, regular water flow, avoiding stagnation. And then I've just taken 2 extracts from the glossary at the back of the L8 document, just to avoid any confusion. This is the explanation of what a dead leg is. It's dead leg pipes leading to a fitting through which water only passes infrequently. And to avoid any confusion, stagnation is exactly what it says in the tin. It's a condition where water ceases to flow and is therefore liable to microbiological growth. So if we take a sidestep and now very quickly talk about some facts about Legionella, and the 2 key things which affect Legionella are temperature and flow. And this slide is an interesting slide which indicates what impact temperature has on our water systems. And we've highlighted here the temperature range between 20 to 50 degrees. And we've highlighted it in red because that's the danger area. That's where the temperatures in which Legionella lives. It proliferates, it multiplies between these, it grows between 20 degrees and 50 degrees. So this is the area where we want to avoid our systems. Going back to the first slide where we'd taken the extract from the water regulations, and we stipulate that stored water has to be at 60 degrees and circulated no less than 55 degrees for healthcare. And that's why those temperatures were decided upon, to avoid this danger area of 20 to 50 degrees. Then at the very top here, you can see that between 70 to 80 degrees is thermal disinfection range. So the bacteria is killed off instantly at those temperatures. So if we now talk about some product technologies to help us as designers and installers to overcome some of this risk for Legionella growth. And one of the areas which has been pinpointed or identified over the last number of years, maybe 5-10 years, has been expansion vessels. And the traditional type of expansion vessels, which are used widely throughout our industry for many sectors, actually have been pinpointed as a potential area of growth for this bacteria, of Legionella bacteria, and such as some of the outputs, outbreaks of Legionella have been identified back to the some of the larger expansion vessels as the key source of bacteria growth creating this Legionella. So as an industry, we've tried to address this, and such as the written within the HTMs and the L8 documentation, is that we now endorse a technology called Flowthrough technology. The old traditional type of expansion vessels, which you would see in every heating system, actually encourages the way they operate, encourages the stagnation of water. They always have a retention of that water held within the bladder or the diaphragm of the expansion vessel. And that's not good. We've highlighted already in the opening slides that we want to try to avoid stagnation of water wherever possible. So within the documentation and guidance, we now encourage and endorse, especially in the healthcare sector, for us to specify and install a technology called flow-through vessels. And this is exactly what it says on the tin. This is a vessel which is encouraging the water to flow through the vessel to prevent that stagnation. So it's designed specifically to have an inlet and an outlet. And what happens on every pass, the water is channeled through the diaphragm or the bladder of the vessel, and it creates a turbulence. And in doing that, on every pass, the water within the standing water, let's call it, or expanded water within the vessel, is replaced with fresh water from the incoming mains. And by doing this, we reduce the risk of Legionella. We're in full compliance with the L8 HTMO4 documentations, and it's seen as the best guidance what we can do. Now, I wouldn't say that this is exclusive for the healthcare sector, and we see this now being replicated in other sectors throughout our industry. Now, as specifiers, it's vitally important that when we're specifying a flow-through technology or a flow-through vessel, that we ensure that it works and it's tried and it's tested. And you can do that by including within your specification text that it must comply to or be tested to the DIN standard of 4807. And in layman's terms, it's a salt test. We fill the expansion vessel with salty water, and after a few passes, we basically do a salt test on the vessel to ensure that the salty water has dissipated back into the system. And we've got some instances at the minute where some companies are offering individual components where they attach them to the existing potable vessels, but they're not a tried and tested solution as a complete package. So I would majorly encourage you guys to include a solution, a package solution, to include the salt test if you're going to be creating a spec test for this particular product. And again, talking about sizing and selection of expansion for our potable systems, there's some issues in the industry whereby on the potable side, there's a lot of instances where the expansion vessels are largely undersized. And it's for a number of reasons, but one of the main reasons is because some of these unvented cylinder manufacturers supply as standard their unvented cylinder with a predetermined unvented kit, which includes the expansion vessel. And we've been doing a lot of tests and checking of late, and the majority of these guys would actually only supply an expansion vessel which will accommodate the expansion within their cylinder. What they don't know at the stage of when they're buying or manufacturing in bulk is the size of the systems, because these are supplied in bulk through the merchant groups. So one thing as a designer, as installers, what we need to be very careful, we need to do a recheck of our sizing and selection of expansion vessels within the potable sectors. And again, I would highlight that we should be now, for all sectors, specifying flow-through technology for the expansion vessels. So here is a slide which indicates some of the critical criteria which we need to accurately size our expansion vessels on the potable side. And the four key criteria are system volume, system temperature, and that's the maximum temperature. So we need to know a little bit about the system after install. Are we going to implement a thermal disinfection module? If that's the case, then we need to ask the question, at what temperature will you be thermally disinfecting your systems? And that determines what system temperature we utilize. We always work on the worst case scenario or the highest temperature scenario. We then need to identify what the cold fill pressure is, or the static height. So this is largely, for potable, is largely determined by the pressure reduction valve setting, and generally would be supplied as part of the unvented kit at a 3-bar PRV setting. So that is your incoming pressure. And then we need to know and identify what the maximum working or safety relief valve setting is for the system. And generally, again, for potable, it's generally set at 6 bar for a safety relief valve as an integral part of the kit. So then on the right-hand side of your screen, you can see this is actually taken directly from the Flamco size and selection software. And we fill in the pink fields, with the system volume, what the fluid is, if it's water with glycol. And of course, for potable systems, it's always going to be water. The highest fluid temperature, we're basing it upon 70 degrees. And then we've got two important features or factors to build in here is the fill pressure, which is 3 bar, safety valve, which is 6 bar, and those two figures determine what the working range is for our system, and it also determines what the pressure efficiency, or commonly known as the acceptance factor, is of the expansion vessel. And this is again a common mistake utilized by installers, designers, is that we calculate what the expanded volume is. So from this criteria, we can identify that the coefficient of expansion based on science is 2.28%. And again, based on science, that expanded volume is 90 litres. So on a lot of occasions, we've seen installs where the installer has just said, well, expanded volumes 90 litres, I'll put in a 100-litre expansion vessel. And what they haven't taken into consideration is this pressure efficiency or acceptance factor. And what this largely means is that we can actually only utilise, because of the working range, the 3 to 6 bar, we can actually only utilise 35% of that expansion vessel. And that needs to be an important integral part of our site selection process. If we look at the midsection here in the tables, we can see that the expanded volume is 90, and when we apply the formula utilising only 35.7% of that vessel, we then identify that the minimum vessel size for that specific project or system parameters is actually 253 litres. That's what we need from an expansion vessel. We can't get a 253-litre vessel, so you always go up a size, and from here you've got the option of going for a 300-litre, what we call Airfix DE, which is a potable flow-through expansion vessel. Then in the background, we've got the working formulas, if you want to double check on how you physically came about determining what these figures are. So just to reiterate on potable sizes, always recheck and don't just take what the manufacturers of the cylinder supply as adequate to accommodate the system volume as well. So we're going to run into another technology which helps us create a balanced system, and opening slides dictated or determined that balancing is a critical part of our design criteria these days. And one way of achieving that is by incorporating thermal balancing. So if we go back a step and say, why do we need thermal balancing? And we need to balance our systems because it's getting back down to the basics of water behavior. Water follows the path of least resistance. So if you can see here, these two crude drawings or sketches, and they show what would happen on a system if we've got zero means of regulation or balancing our system. So you can see here, you're going to have hot spikes on the shorter circuits, and you're going to have cooler spikes or cold spikes at the end. So water follows the path of least resistance. So in this type of arrangement on the left, it's going to be near impossible to be compliant to your L8 regulations, in that it stipulates that your taps have to have hot water at 55 degrees in healthcare within 1 minute. Depending upon the size of the system, but you're not going to be able to achieve that. So on the right hand side, this is what we want to see. And this is a nice balanced system where you've got hot water being hot as close as we can to each outlet. And the only way to achieve that is by incorporating the technology called thermal balancing. And these are the thermal balancing valves installed on the return legs coming back to your plant room. And these operate automatically to ensure that each of these subordinate loops are balanced thermally and dissipate the heat or the energy evenly throughout the whole system. So again, just to reiterate, and to reiterate why we need to be in compliance, or what the compliance stipulates in relation to balancing our hot water systems. And again, throughout your HTMs and the L8, it's avoiding water stagnation. So we want to encourage flow. It's not just about temperature these days, it's about temperature and flow. We've got to eliminate those dead legs. Where you've got dead legs, there's a stagnation of water. And if the water's stagnant, it's going to fall into that danger zone from a temperature point of view between that 20 to 45 degrees. And we've got to avoid those water temperatures between 20 to 45 degrees. And the only way to do that is by thermally increasing our temperatures and making sure there's adequate flow in our systems. So if we quickly look at what the recommendation would be specifically for the healthcare sector, and the healthcare sector is more stringent in reducing the dead legs. Yeah, and it's more stringent about creating flow as close to the outlet as possible. And this would be a typical extract from one of the HTM documents to say how you would pipe up a typical ensuite, let's call it, for a hospital or a healthcare environment. So what we've got here, we've got your domestic hot water supply coming down, yeah, from your main subordinate loops. So we're coming down, and this would be your tertiary loops. And then we're returning back up into your sealing void and coming back into your subordinate loops and back to your plant room. So this is the circuit This is your hot water return circuit, which is circulation. So you've got 50, let's call it 55 degrees, 60 degrees and 55 degrees coming back here at any one time at this point. Now, there's a misconception or a misunderstanding in the industry in relation to dead legs. A lot of people stipulate that the dead leg is actually the point after the thermostatic mixing valve to the outlet, and that's not true. The dead leg in this occasion is actually from this point, the point after your hot water return connection to the outlet. That's your dead leg, and that's what we want to try to reduce as much as possible. Now, for other sectors, which wouldn't be as stringent, it's not as high risk, let's call it, as the healthcare sector, you would get away with more ring main, let's call it, or subordinate loop mixing and thermally controlled. So on this application on healthcare, we're mixing right down to the appliances. On other sectors where it's less high risk, you've got your hot water flow coming up and you're picking up maybe on your last outlet and you're recirculating, coming back to your main return line back into the plant room, so that this leg is guaranteed to be balanced and you're coming back at your 55 degrees or 50 degrees, let's call it, back into your plant room. So this would be an acceptable situation whereby you've got a less high risk application and you're you're balancing the main lines as opposed to your tertiary lines. But the main thing about both of these applications is that when you turn on a tap on any of these applications, that you got to have hot water to your thermostatic mixing valve within 1 minute. So if we have a quick look at how these devices physically work, and the key component part is a wax thermostat within the body of the thermal balancing valve. And the wax thermostat reacts, it's a sensitive wax thermostat which reacts to temperature change. So the hotter the water which surrounds the thermometer gets, the more it expands. And when it's expanding, it's regulating down and it's causing more resistance on this specific leg or in the valve body. And as we know, water follows a path of least resistance. So if we're creating more resistance on this particular valve or on the branch, we're going to dissipate that heat or that balanced hot water or energy to another part of the system which needs it. So then when this leg starts cooling down to, say, 55 degrees, the valve creates less resistance in that it contracts, yeah, and it's saying, heat me up again, guys, you know. So then the hot water comes through, providing there's no restriction through. And that's how this thermal balancing valve system works. If these are all adequately and properly positioned throughout the system, you will get an evenly balanced hot water return leg. Now, these valves have to be installed on the hot water return legs. They cannot be installed on the hot water flows, and that's a critical, important part of the design feature. So just some other points to make as specifiers, you know, what's important to include within your spec test. These valves need to be automatic by operation, and they need to be automatic because years ago when I first served my time, as a mechanical engineer, I was involved in a hospital job up in County Antrim, and we spent weeks and weeks and months trying to balance the valve through means of manual regulation. And on such a vast hospital site, it's impossible to do, and it's impossible to manually balance a potable hot water return circulating system because of one fact, and the fact is that the dynamics are constantly changing because of draw off. You're fine up until the point of someone opens the tap, and then all of that hard work you've done is messed up because the dynamics have suddenly changed because you're taking water out of the system and you're entering in new fresh water into the system. So it's very unlike a sealed heating system or chilled water system. So the only way to physically be able to balance a big system, a large system, is by means of automatic thermostatic regulation. Some manufacturers offer a component part which is very useful to have from an isolation point of view. So this device shown in the picture has a manual regulating stroke isolation valve, which is good for servicing and retrofit work. Also, an important feature to include is an insulation jacket to provide some insulation for heat losses, against heat losses. And one important feature, which I would always include in the specification text as a standard a standard within the unit is disinfection module. I explained how these thermostatic balancing valves operate. So the hotter the water gets surrounding this, the more it regulates down almost into the closed position. Now, if we've got a thermal disinfection module or strategy in place, we're actually increasing the temperature at source to say 70 degrees, and we want that 70 degrees thermal disinfection temperature in as many parts of the system as possible. So really, we don't want this to be regulating down. So this is a clever device in that it's got an inbuilt bypass. It detects 67 degrees Celsius, opens a bypass and lets it flow through so that we can carry out a thermal disinfection module within the application or within the premises. And of course, then thereafter, we need a gauge just to verify a commissioning and from a servicing point of view what the temperatures are on our return circuits. And here I would just like to highlight one point. This is an extract we have taken directly from the HTM, the latest HTM 04.01. And if we look up to here now, it actually stipulates what I've been saying over the last two slides. It says that hot water supply return regulating valves shall be automatic in operation. So that just verifies my point about we cannot get away with manual commissioning valves on a potable hot water circulation system these days. It has to be automatic in operation. And just to reiterate, and that's purely because of one thing in these hot and cold water systems is draw off. Okay, so now we're going to go into another interrelated to thermal balancing is pressure control. And we'll talk initially, just the introduction, said why is pressure control a requirement in our systems? Why do we need to make it a consideration? Well, if we've uncontrolled or excessive pressure, it's going to drastically reduce the life cycle of our appliances and system components. So with wear and tear, the higher the pressure, the more wear and tear you have. And the higher the pressure, the higher the flow. So we've got a lot more water wastage, and we're now becoming a very sustainable green industry, and water wastage is a big no-go. And of course, from a user comfort point of view, we have all probably experienced when we're in a pub or a nightclub and we've put on the tap and there's got that excess, we've got too much pressure and the water overshoots the base and it spills over your nice beige chinos and you look a bit of a sight on the dance floor thereafter. So, and ultimately, with uncontrolled excess pressure, we're designing systems which are inefficient and largely oversized. So what's the solution? The solution is pressure reduction valves. And these pressure reduction valves do exactly what they say in the tin. They take an upstream pressure and reduce it downstream of the device. And with these positioned correctly throughout our schemes, we're going to create a system which has less wear and tear of the fitment. So we're going to increase the longevity of our systems. And of course, the user comfort, you don't have that splashback embarrassing situation. And these devices, we're reducing the pressure. We don't have that instance where you're wasting a lot of water. So they're seen as an economical use of water, and they're recognized by BREEAM as water saving devices. So if we just look now about the role of pressure reduction valves, and this seems a very basic slide, especially to some of our engineers attending today, but I make no apologies for showing this because some of the conversation we have with installers and others is quite eye-opening. So we need pressure to move water from A to B. So we need pressure in this type of arrangement here. We need our boosters to overcome the static resistance of the static height of the building to enable to push the water from here to the top floor to serve our appliances. Now, what we've seen, and I've seen this quite recently in practice, is that some installers think, well, we're going to save money. On this occasion, we've got PRVs fitted on the cold water system on every single floor. Why don't we set one PRV in the basement, set it at the desired outlet pressure, let's call it 2 bar, and you've got 2 bar in all parts of the system. And what they've neglected is the static loss and static gain, I suppose. And it needs to be a key consideration. And when we're selecting these valves, it's critically important that we select any elevation change within our systems, floor by floor, that we do a reselection to ensure that the appropriate valve is selected. So if we take a step back and show you a cutaway version of these PRVs and explain, I'm going to explain very briefly on how they physically work. And one important thing about PRVs is that they're largely in this type of application, they're largely designed to be in the closed position. So what we've got here, we've got a high pressure inlet, say 8 bar, coming through the PRV, and our desired outlet pressure is, let's call it 2 bar, feeding our taps and our showers. And if you think about it, in a hotel or a leisure centre or wherever else, you know, the taps, and even in your home, the taps are largely in the closed position. That means that the PRV is in the closed position. So these devices are designed to be in the closed position. And how they physically operate, when there's no demand from your taps, it causes a back pressure which acts upon the valve seat. It overcomes the torque or the pre-calibration of the spring in the headworks, and the valve seat is allowed to close. When it closes, it has to be what we call drop tight by design, and that means it's fully sealed. And when it's fully sealed, it means that there's no pressure creep, there's no ingress of water from the high pressure side to the low pressure side, and that in itself is a true pressure reduction valve. Okay, so the key thing about a quality pressure reduction valve is the technology in and around the valve seat, in that they're created, designed, manufactured so that they're drop tight by design. And the way to ensure that your valves in your specifications comply to that and they're a true PRV is if you specify the BSEN 1567, it's one of the criteria within the testing procedures under that standard. So if you specify that, you're going to be guaranteed to get a quality pressure reduction valve, which is drop tight by design. So this is the cutaway version of what's happening when it's in the closed position, when there's no demand, when everyone's in bed, no one's turning on their taps. So then suddenly somebody gets up and they open a tap, or they get in under the shower. So what happens on the outlet side? Someone opens that tap, and that pressure, that back pressure, which is acting upon the valve seat previously and closing the valve seat, is reduced. Yeah, as soon as you open that tap, that back pressure is reduced. The spring pre-calibration overcomes the valve seat, and the valve is allowed to open to pass through a proportion of water from the high pressure side through to the low pressure side to satisfy the demand of each of those outlets. So that's what happens on the outlet position when the valve is in the open position. And the critical thing for the majority of applications is to ensure that the PRVs control pressure on both flow and, probably more important, under no flow conditions, because that's when it does the majority of its work. Now, one thing about PRVs within our industry, there's been a few instances over the last lot of years, and PRVs can be noisy if they're sized and selected incorrectly, and I'll touch on that in the next 2-3 slides. But one critical thing which we've seen more and more often, we're in a cost-driven situation, especially now with the inflation of prices, and we're seeing a lot of domestic PRVs feeding their way into the commercial arena, and that's why it's critically important to stipulate and get your specification text right to avoid having a domestic PRV feeding its way into a commercial application, which can be a recipe for disaster because they're not really fit for the vagaries of the commercial sector, let's call it. So one way to protect ourselves as designers, as clients, as installers, is to ensure firstly that our spec text includes, or the valves include, a regulation for the water supply regulations. So we can do that by ensuring that it comes with either RAS or KIWA approval. I'd mentioned previously, if we ensure that it's a BSEN 1567 compliance, it'll ensure that it's fully tested, it'll make sure it's drop tight performance, and more importantly, it goes through a series of acoustic performance tests. So by specifying these two things, that we mitigate a lot of the risk of getting a domestic type valve installed in a commercial arena. To take things a few further, to take things further, I would also ensure that it's a commercial valve by stipulating, especially on the high pressure side, that we go with a threaded connection as opposed to a compression connection, because some of the pressure haunts and the pressure increases in water hammer can, on some occasions, we've seen the compression ring come loose and you can have full bore failure on a high pressure system, which can be catastrophic for everyone and a building. So again, just trying to protect your specifications, protect the end user, protect the clients. With regards to sizing and selections, I can't stress this enough. You know, sometimes we see a lot of installs, a lot of designs, which are basically a one size fits all. And what I would say is that every elevation change, every change of floor needs to be resized and reselected. The key important thing for sizing and selecting pressure reduction valves is our delta P setting. And when I say delta P, it's the differential in pressure from your incoming and your desired outlet pressure. Your desired outlet pressure should never change. We want to have user comfort on every floor. We want them to have consistency in supply so that if they're in the top floor or the bottom floor, the taps are delivering the same amount of pressure. The variation comes with the incoming pressure, you know, and again, that's through your static loss and static gain. So if we have the schematics, you know, we can make rough guesses or we can make best guess with regards to how or what the incoming pressure is going into each of the valves. From that, we identify what the delta P setting is. So if you've got, let's call it a 6 bar incoming pressure, and we've got a desired pressure of 2 bar, you've got a delta P of 4 bar. Yeah. From this, you know, we know that a 1-inch valve is going to be delivering 15 meters cubed per hour. Yeah. So that would satisfy your maximum peak load demand. 15 meters cubed per hour for, in today's language, is 250 liters per minute. So that's how they're largely sized and selected. But the two important things is that, one, the valve selected must be able to cope with the peak load demand, but it also must be able to cope with the low flow demand as well. And that's an industry issue, whereby some of the manufacturers are good on the peak, mid and peak loads, but they're not so good at controlling pressure on the low flow demand, especially when there's a high turn down ratio. And I think the next slide will explain what the high turn down ratio is. So every manufacturer should be able to produce a cavitation curve. Yeah, and this is something every valve you select, you must cross-reference to ensure that your selections are within the safe or the recommended operation zones. Yeah, so if we've got an example of, say, a high inlet pressure of 10 bar, hopefully you can see my screen okay where the laser is at 10 bar, and our desired outlet pressure is at 2 bar. If you put in a standard valve, they're going to be in the cavitation zone. So that valve is going to cause cavitation, it's going to cause vibration, it's going to cause you, your client, the users, a bit of a nightmare in these systems. And we see it all the time. We hear about it all the time, especially in hotels when there's people at nighttime, 3 o'clock in the morning. This is when all the noise comes, because there's one person gets up and they gently open the tap and they're only calling for 3, 4, 5 liters per minute, and they've got a big valve trying to deliver 3, 4, 5 liters per minute, and they've got a big high turn down ratio going from 10 bar down to 2 bar. It's a recipe for disaster. So that's why Premier Inns are paying out a lot of money on some well-known sites because of PRV noises throughout the night on low flow and on high turn down ratio. So make sure you get your high turn down ratios right. Make sure you verify with the manufacturer each selection of valve per floor, and that's how you cover yourselves to ensure that you've done all you can to mitigate any risk of noise within your systems. One way of overcoming a situation, again, just to follow on from the previous slide, if you've got a very high peak load demand, yeah, so we're coming up with a riser here or a branch coming out and feeding a lot of hotel en-suites, and this is, let's call it a 4-inch or 100 mil pressure reduction valve, which is fine for meeting that peak load demand. But again, what happens in low flow demand? The low flow demand actually says that this same 100 mil valve, which is which is comfortably doing 500 liters per minute. But we're also asking the same valve to control pressure under 4-5 liters per minute. And what actually happens, the valve, the PRV, as if you can remember how I explained the opening and closing of the valve seat, that valve seat is barely opening, right? And when you've got a high pressure going through a very small aperture, you're going to cause erosion. Yeah, and it's called draw wire. So there's erosion on the valve seat. So then there's a permanent pathway for the high pressure side of your PRV to infiltrate into the low pressure side. So it's not a drop tight PRV. So you might as well take the PRV because on both sides they will eventually equalize. So one solution you can consider is putting a bypass arrangement in, whereby this is the master PRV, and the master PRV will meet the peak load demand. And you put in a bypass arrangement, a smaller valve, which will cope with the low flow rate demand. So that guy opening up the tap at night, this valve will kick in. And how you kick this valve in first is that you would generally set that at half a bar higher than the master valve. And by doing that, it's encouraged to open first. And that's a very acceptable solution, which we've seen on a number of occasions working correctly. But what I would encourage you guys is to liaise with the manufacturer, make sure that the valves are selected are not within the cavitation zone, and also ask the question, is there a bypass arrangement required in order to meet the low flow demand? Now we're just going to talk now just about some, again, industry issues, and a lot of the industry issues are surrounding hot water systems. As I mentioned, a PRV is largely designed to be in the closed position, and the PRVs are not designed to be in circulation systems. Okay, and this is where a lot of problems originate. Now, if we go back a few slides, whereby the healthcare sector are trying to really reduce those dead legs, and the point of the dead leg is after the hot water return connection. So if I can just maybe expand out here. Yeah, if we look at this here, so your hot water return connection is here, right? So what we're finding in our industry, and again, as part of the AL8 HTMs, we're trying to reduce the dead leg. So the dead leg is from this point to your last outlet, you know, which on a lot of occasions would be unacceptable. So this return connection is getting closer and closer to the outlets, right? And what it's actually doing, it's actually limiting, reducing the positioning of pressure reduction valves. Now, this is a live example of a job I was called to, whereby the contractor said, we've put in the PRVs exactly as per design, and we've put in all the valves as per design, but we're not getting any hot water circulation coming back to the plant room. When I quickly went to the site, I realized that they had put it in exactly as per design, and the design had PRVs on everywhere. Great for sales, not great for performance. So the problem here, it was fine on the cold water side, because the cold water is against a dead head, let's call it. It's non-circulating. Whereas on the hot water supply, they've got it on the wrong side of the hot water return connection. So it's on the circulation side of the return connection. So what is happening here? You've got your, say, 10 bar coming in. Your PRV is reducing down to, let's say, 3 bar, and then we're coming back in the return leg, and we're trying to get back into a 10 bar return line. And that's where the flow is stopping, and that's why a lot of occasions on the hot water systems, we see a lot of circulation problems on the hot water return circuits, and it's largely down to the PRVs being installed on the circulation side and not on the non-circulating side. So the solution for this particular one was to take out the hot water return PRV. It's never required. You should only be fitting a thermal balancing valve on this occasion there. And taking out this particular PRV on the hot water supply branch and moving it to this side of the hot water return. So the hot water return is balanced. From a pressure point of view, you have 10 bar, 10 bar, 10 bar, and then you're reducing your pressure thereafter, feeding your appliances. So that's something just to be aware of on the hot water circulation side of things. So correct PRV positioning within hot water circulation systems is critically important. And let me just move Steve's face there. Then PRVs must be installed downstream of the return connection. So that's the two important things to take away from the hot water circulation issues. Again, if you have any schemes you want us as Flamco to run our eye over, we're more than willing to do that, because it is becoming more and more of an issue because of the stipulation for the reduction in dead legs. So now just the final slide is just a summary of what we've talked about here. So from a PRV, pressure reduction valve selections point of view, ensure the valves can accommodate both the maximum and minimum flow rates. Oversizing valves can cause noise and system vibration, and they can also cause that erosion, the impact of draw wire, which I explained, it's erosion on the valve seat. PRV hot water recirculations, we've said it, must be installed downstream of the return connection. Thermal balancing valves are essential to achieve L8 balancing requirements, and avoid stagnation in vessels by utilising flow-through vessel technology. And one thing, if you don't remember anything from today, from an overall design concept point of view, the most important thing to remember is keep the hot hot, keep the cold cold, and keep it moving. So that ends the presentation. I want to thank you all for listening. Thank you for attending, and I would now invite any questions from the attendees. Thank you.
Yeah, thanks, Stuart. Very informative.
Thank you, Steve. Appreciate the opportunity. Yeah. Is there any questions, Steve?
Yeah, there is. Chris has made a comment, and he said, great presentation. Am I right in that there are a number of industry issues? So one, it seems difficult to roll out technically precise designs, and two, he says, make them affordable and predictable. And do we need to regulate more to ensure that the market complies?
Absolutely, yeah. Chris, I fully support and agree with what you've said. I've got 20 years experience on the potable water side selling these valves, and the industry issues are only expanding and getting more and more. And one side of the coin is contradicting the other, if you like. We're changing the regulations. We're actually trying to be smart with regards to reducing the dead legs and, trying to create flow right up to each of these taps. But it has a knock-on effect on valve positioning as well, and that's not addressed within the regulations and within the guidance. And that's overall the big problem. That's what's causing the issues. And people are traditionalists. The installers will always fit a PRV, a hot water PRV, right beside the cold water PRV. And if they're doing that today, the hot water PRV is in the wrong position because it's going to be on the circulation side of the hot water return leg. And why is that? It's because we're telling them to put the return connection as close to the outlet as possible. So it's a catch-22 situation. And Chris, I think your question or your statement is fantastic, and I fully endorse and agree with what you're suggesting. It needs to be more regulated, and I think there needs to be more communication when we do change the steering committees for the HTMs and whatever else. I think they need to liaise with industry a little bit more so that we can address these, let's call them, knock-on effects. But thank you, Chris. I really appreciate your comment.
Great response. Thanks, Stuart. Question from Phil on flow-through vessels. What is the largest connection size available?
Every manufacturer is different. I think, I can only speak, unfortunately, on behalf of ourselves, and I think we go up to a 2-inch. I'll verify that, in writing to you, Phil, afterwards. Now, on some, what we do is we actually test the vessel with the connection as a one-piece unit. I maybe didn't explain it great within the presentation, but one of my points I was trying to indirectly make was that there's a lot of devices in the industry at the minute where they just say, well, you can fit this device onto an existing potable expansion vessel, and they're available up to 1 inch. I'm only aware of them up to 1, maybe 1.25 inches. And what I've seen is that you've got 1.25 inch connections called anti-Legionella valves being fitted onto huge vessels, and they're not tried or tested, and they're not working, you know, so you're not achieving the results you want to achieve. And that's why I highlighted the fact of the importance of, when you're specifying a flow-through expansion vessel, to make sure that it's tried and tested, not just the vessel, but that the flow-through technology is compatible with that specific vessel. But with regards to sizes, I think the actual outlet on ours is roughly about 2 inch, but I'll come back to you on that, Phil. Thanks for the question.
A response from Chris, thank you for your answer. And he asked, we urgently need clever in the parts that get fitted, a bit like the way the aviation changed fuel non-return valves, so they could only be fitted in the right way round. So a little arrow on the valve would, I think that's what Chris is referring to.
No, absolutely, yeah.
Yeah. Quite a broad question from Andrew. What are the rules for existing domestic hot water and cold systems? I think that's referring to the temperatures that you spoke about and achieving those recirculation temperatures. If you could just go through that again, Stuart.
Yeah, well, we just need to be in compliance with Elliott to make sure that the return temperatures are coming back, and that, I suppose, you know, that we're in compliance with our Legionella testing regimes. So, you know, a lot of it's reactive, you know, so that if the tests come back and there's high ratings of bacteria growth within the system, then there's remedial works need to be put into place. But I think, you know, moving forward, if the systems are maintained and they're within the allowed parameters, then we're okay. There's not a stipulation that we have to go and retrofit all of these vessels and whatever else.
Yeah. And again, within the cold water systems, is there maximum temperatures that those systems are allowed to rise to?
Yeah, well, it's a very interesting point, and it's an area which I know a lot of manufacturers, us included, are really looking closely at the minute. And under the Elliott guidance, the stipulation is that the cold water needs to be kept with below 20 degrees. Yeah, now there's technology out there which is available to help achieve that, the likes of dump valves. So they're dump valves connected into a sensor, so that when they sense that the temperature is increasing above 20 degrees, that it goes to dump. You know, and you're pulling in fresh water until the mains water comes down and the temperature is below the 20 degrees. Now, the big issue we have, and again, this is where we're not being clever as an industry, is that we cannot get those valves approved by the water regulations, because it's seen as, they just do not recognize dumping water at all as it's contrary to what their belief is. And, you know, any device which you promote or put forward for approval, it cannot be seen to be creating wastage of water. So we've had, on a number of occasions, been rejected from the water authorities for some of our suggestions, you know, on how we achieve the 20 degrees, but we're trying to work on various other solutions. Now, I worked with various and a lot of consultants, and I've seen back home in Northern Ireland, there's some healthcare projects whereby they've got circulation systems on the cold water side, and you know, they run them through a series of chillers, and then it's exactly what I explained there on the hot water side in reverse, whereby you've got thermal balancing valves, you know, maintaining that balanced water to ensure that the balance of the cold water is kept within 20 degrees. So that seems to be a solution which is taken off, but again, there's a high cost in that. You know, we're putting in circulation systems, you've got chillers and everything else, you know, into a cold water system. So the increase of capital cost and maintenance is hugely increased, you know, because of that. But yes, the cold water side is becoming an issue, especially on the that's where we do have issues on existing older buildings, whereby there's a lot of heat gain above the ceiling voids, and it's near impossible to comply to Elliott, whereby the heat gain of the pipes is taking the water well above the 20 degrees.
Great, thanks, Stuart. Andrew's just broadened his question a little bit more. He was thinking of old, poorly maintained systems, such as sports clubs and so on.
Yeah, well, you know, for that, again, we got to just do whatever the best practice is to mitigate any risk at all there. So, yeah, we would endorse the refitting of flow-through vessels. You know, take out the existing vessels, put the flow-through vessels. We would encourage, the first thing you would do is a risk assessment. You would just say exactly what they've currently implemented to mitigate any risk of this Legionella, and to try to reduce dead legs. And again, it's just doing a test and just looking at the application and making suggestions on how best to make improvements.
Great. Comment from Charlie. Charlie's a member of the Sophie Yen Young Engineers Network Committee, and this has been extremely beneficial in helping him develop his public health engineering knowledge. So real thank you there, Stuart.
Oh, that's brilliant, you know, and we would absolutely love to do more with Sophie, and if you know you guys can help us out there, absolutely would love to get a platform and help, and you know, be maybe a partner, a manufacturing partner. Would absolutely love that.
Yeah.
So thank you for the comment.
Yeah. Question from James. Would you recommend replacing double regulating valves on existing hot water circulating systems with thermal balancing valves?
Yeah, absolutely. Absolutely, you know, because the double regulating valve hasn't got any intelligence. It's just in a fixed position, and the dynamics of a hot water system are constantly changing, and it's in the fixed position. I know, Steve, you have a lot of experience on the heating side, and you know yourself with static balancing valves versus dynamic balancing valves. There's only one winner. Yeah, so it's the only way to achieve a balanced system is through means of automated thermal balancing.
Yeah. Comment from Andrew. Thank you for your response. And a number of attendees have asked for a copy of the slides and presentation, which will be available on the CIBSE website, and all those who attended the presentation will be forwarded on to them. And of course, I've put Stuart's contact details in the chat box. So if you need him to present at your company, please contact Stuart. So that's the last question. Stuart, thanks very much.
If you are responding or asking me questions, I'm actually on holiday for the next 2 days, but I'll respond to your queries, questions, and comments on my return on Monday. So once again, thank you so much, Steve. It's a privilege to be here today. I really appreciate this type of platform, and I'd love to do more of the same as such, and I'd love to get involved with the Sophie guys also. So thank you so much for attending. Thank you for the questions, and keep in touch.
Have a great evening, and thanks again, Stuart, and thanks everyone else for attending tonight. Have a good evening.
My pleasure. Thank you. Thank you all. Thank you.